Okay, so to evaluate this limit, again, we're dividing the numerator and denominator by the highest power of t in the denominator, and you can see the largest power of t is t to the 1. So what we need to do is a fairly good amount of algebra here. This expression we're going to divide, or equivalently multiply by 1 over t over itself. That's equivalent to dividing the numerator and denominator by t. But you can see, since we have a radical in the numerator here, 1 over t, we have to write an equivalent form of this so that it has a radical of index 2 so that it can go underneath this radical. So 1 over t is the same as 1 over the square root of t squared. Because the square root of t squared, when t is positive, the square root of t squared is just t. So these are algebraically equivalent. But the thing to note is, I just wanted to put the details here so you can see how this goes into the radical. It's really, we're using this property. A product to a power is each factor raised to that power. So this term 1 over the square root of t squared, you can think of that as t to the negative 2 raised to the 1/2 power. Again, because raising a power to a power, you multiply the exponent, so that would be t to the negative 1. T to the negative 1 is 1 over t. So this factor here is the same as what we started with, and it's also the same as this factor here. They're all three different ways to write the same thing for t positive. So this is a convenient way to write it because when we write 1 over t in this manner, we can see that the exponent is a half, and this exponent of 1/2, and then we have the square root of this expression, and that exponent is a half. So we're using this property. We have a product each to the 1/2 power. So then that's equal to the product, the product raised to the 1/2. So that's what happens here. So it's 25 t squared minus 125 times t to the negative 2. So this is a direct application of this power, of this property of exponents. And now that it's written in this way, we can apply the distributive property. So this is a sum, and so t to the negative 2 multiplies each of the terms in the sum. So when you multiply t to the negative 2 times 25t squared, when you multiply, t is it's the same expression, so you add the exponents. So you'd have t to the 0. T to the 0 is 1, so that leaves the first term as just 25, but the second term is this term, 125 t to the negative 2. So that is the numerator. So I did write out, well, that's where we'll end up with the numerator. I wrote out, I guess, a little bit different here. This square root, can come in the denominator. It's because of this property here. So we have that, and so we end up where we left off over here. Dividing by t squared, this is a 1. Divide this by t squared, you have this term. And in the denominator, it's a whole lot simpler. T over t is a 1, minus 5 over t is here. So now, as t goes to infinity, what happens? Now we're in a position we can take the limit. So as t goes to infinity, this term, oh darn, let me go back. I didn't want to do that. I'll just leave it like this. Anyway, what happens? This term, as t goes to infinity, this term goes to 0. This term goes to 0. So what's left is the square root of 25 minus 0 over 1. The square root of 25 is 5. Here, there is no t, right? When limit t goes to infinity, that just sent both of those terms to 0. Here, there's no t here. This is just a constant. So it's unaffected by t because there is no t. So the square root of 25 is just 5. So this limit, the original limit, is just 5.